Oh, you're here! Welcome back to the shop, I guess. It's time for another Machine Building Basics video. I'm Oscar, and this time we're talking about motion systems. So let's head on over to the bench and look at some examples. So first up we have rails and carriages. And there are of course a couple of different versions of rails and carriages depending on our needs and the machine we're building. Now in the context of CNC machines there really are three main avenues we can look at. And the first one is really the cheapest and simplest and most hacky version to achieve precise linear movement. And that is basically just aluminium profiles like this one. Now on several types of machines, like the Workbee and the open-built C-beam machine and a whole host of other machines, the linear rails are actually aluminium extrusions with plastic wheels running on them. And this works fine for low load requirements, and for small hobby CNCs or for 3D printers, it's perfectly fine, but I would not use it for more demanding work. Other useful applications are like camera sliders or pick and place machines, things with low load and low speed requirements, and semi-low precision requirements. Because mechanically speaking, sure this rail looks really straight, but if we're talking about high precision CNC machines, it's not. So one step up from the aluminium extrusion as linear rail is the round bar rail. And this is actually a rail that was left over from when I built my 3D printer. And hardened round linear rails are actually used in some fairly high precision machines. But the same thing here is true as for the aluminium extrusion version. Things with low load requirements are generally better when designing something for round rails. To be able to take the same loads as square rails or high-one rails, they will need to be oversized. And there are a couple of different versions of linear rails. There are free-floating linear rails, as here on my 3D printer, that is extremely dirty by the way. There are also supported versions of linear rails, where the rail itself is bolted to an aluminium extrusion, either at a height or directly in the groove, like here, and then have two wheels running, one on top and one on the bottom. These type of rails are better and can take higher loads than the free-floating ones, but they will still need to be oversized to have the same load-bearing capacity as square rails. And these types of supported round rails works okay for small to mid-size CNC machines with low to medium precision. And when I say low to medium precision, I'm talking a couple of tenths of a millimeter. Because if we're talking CNC machines and if we're talking precision, then really you want to be down at 10, 20 or 30 microns. I just want to put that out there first so you don't get the wrong impression of what I'm talking about. So, but what are square rails then? Well, square rails come in many different shapes and sizes. This is one of the smaller versions. This is an MGN12 I bought for a 3D printer project I never completed. And as you can see, they are square. And this rail is hardened and ground into very, very fine precision. But a square linear rail is only as precise as the material is bolted to, because they are fairly long and fairly slim, so if you bolt them to a bent piece of material, well, the rail will be bent and your precision will suffer. Now the upsides compared to round rails are of course like I said, higher load bearing capacity, and they are also excellent at taking loads axially in this direction and even twisting like this. And inside this carriage here are two rows of circulating balls. So this is basically ball bearing running on hardened ground rails. So both for high speed and high precision, this is definitely preferable. And that is exactly why I chose the Queen Bee Pro when I decided to build a CNC. Because on all four axes we have hardened and ground 15mm linear rails. Originally, this machine is based on a Workbee, and the Workbee have the first version of linear rails I talked about, which is namely aluminium extrusion with plastic wheels on it. And I see I need to do some maintenance here. And in my mind, even cheap Chinese linear rails are more precise and higher load bearing and more capable than the most expensive type of aluminium extrusion with plastic wheel on it. But it of course comes at a downside of being more expensive. And you know how I said that they come in all shapes and sizes? Well, here is another version. This is a Hiwin RGR30, and that means that it's 30 millimeters square compared to the 12 millimeter, this small baby one. And I'm hoping that these rails will one day be an epic home-built CNC machine. However, I really don't have the funds right now to build it. But these will stay in storage until I do. And now that we have a really precise way to achieve motion from point A to point B while taking high loads in all directions, well, how do we achieve that motion? Well, first of all, of course, we need a motor, which I've talked about extensively in previous parts of this series, so check a link somewhere around here. But how do we attach the motor to our motion system? Now, probably the cheapest way of doing this is attaching a belt. And don't be fooled by the simpleness or the cheapness of it. Belt drive machines are everywhere. We have 3D printers, we have CNC machines, we have pick and place machines. At work, we have roll replacing robots for our cold roll mills that uses belt drive. And as an example, we have the X-axis of my small CNC machine here. And it basically consists of three components. We have the input pinion from the motor, we have the belt, and we have a pinion or some type of gearing to turn it over in the other end. Or we might also have a static belt and have the motor fitted to the actual carriage. And I'll post some pictures up on here on how that looks like. And in my mind, this is actually a surprisingly good way to achieve really precise motion at really low cost. Now, they are excellent for precise movement with small loads, and with small loads you can also achieve quite high speeds with them. The downside is that you can't really accelerate any heavy loads with this system, because the belt itself will act as a rubber band. Especially if you have heavy loads and accelerate them at high speed, then when you try to reverse the motion or brake, the belt will act as a rubber band and tension, which will cause the load to start oscillating back and forth on every turn. And I actually had exactly this problem on the Y-axis of my 3D printer when I built it. Since the Y-axis is fairly heavy, whenever I turn the motion on it, I will get a ripple in my 3D prints. And that is why I swapped out the belt drive for a ball screw. This is a 12mm ball screw. And this is basically the equivalent of the linear rail. We have a hardened and ground thread, we have bearing blocks in each end, and inside the nut we have recirculating balls, in the same way that we have recirculating balls inside the carriage of a linear rail. Now, ball screws are excellent when we're talking precision. Then they are also excellent when we're talking speed. You can run them at incredibly high speeds and high loads. And they are used in almost every different type of industrial CNC machine out there. Now, they do have the downside of being expensive, and they can also be fairly hard to find in lengths longer than 12 or 1500 millimeters. But anything shorter than that, and if you have the funds for it, I would suggest that you use a ball screw. Now, one step down from a ball screw, we have an Acme thread. And in this case, it's an Acme thread with brass nuts. On my Queen Bee CNC router, I have the same type of Acme thread, which is 4 start and 8mm pitch. But instead of using brass nuts, I'm using plastic nuts. It's some type of nylon or other engineering plastic. I'm not exactly sure which type it is. Now, I think Acme thread rods and plastic nuts are a good compromise, because they are not as expensive as ball screws, but you can achieve almost the same type of precision. And you can't really achieve the same type of speeds with Acme threads as with ball screws, because the thin ones will start to whip at high RPM, and you will also have more friction from the nuts. And you will always have more backlash in the nuts on Acme threaded rods than on ball screws as well. However, these are a lot easier to find in longer lengths. I have, without too much of a problem, found Acme threaded rods in lengths up towards 3 meters. So they are absolutely an option for bigger CNC machines, and especially if maximum top speed isn't your primary concern. Now, apart from ball screws, Acme threads or belt drives, we have one more way of achieving motion that is quite common. And that is a rack and pinion. Now, it has both a couple of upsides and also a couple of fairly big downsides. They are still used in industrial CNC machines, especially for the really big ones, and you can manufacture them in basically any length you want. However, they do have the downside of being less precise because the gears need a slight bit of backlash to actually work properly. If you mesh the gears so tight that you don't have any backlash, you won't achieve any motion. You will create too much friction between the rack and the pinion. They also have the upside of not having any whip on higher speeds, as the Acme threads or even thin ball screws have. So you can run the pinion at basically any speed you want. Now, they aren't used in small high speed or high precision machines, both because of the backlash, but also because the racks and pinions can wear out quicker than ball screws, since neither the rack or the pinion is as hard as the ball screw itself, and lubrication and proper maintenance is really important. On some types of CNC machines, I would even prefer a rack and pinion solution, mainly plasma cutters. Because for one thing, micron levels of precision aren't needed on plasma cutters. The actual plasma arc itself will bend and flex and create more slop in the system than the rack and pinion drive would ever do. And since ball screws are extremely precise, they are also fairly sensitive to dirt and debris. And if you ever want to look at a dirty or worn out machine, go look at a plasma cutter in a metal workshop. Even if you have a water table underneath the plasma cutter, it is basically inevitable that you will have metal shavings and arcs thrown everywhere, even on the ball screws, and that will wear them out prematurely. That is actually all I had to say on this subject. Like I said, a really short video. But really, I don't think you need to know much more about this at a glance to achieve some really good results in your own machines. Now, of course, there are tons of more information on all of these different systems. Now, and whenever you design a machine or a motion system, you of course want to take all the loads into requirement. But after you have chosen your motion system, let's say linear rails with a pinion drive, then you can start calculating the load requirements and the sizes needed. This was only a brief introduction with the main pros and cons of each system, and they should enable you to make a better informed decision on what you want to have on your machine. Now, if you like what you're seeing, you know what to do. All the information is down in the description as usual, and till next time.